When dealing with multi-motor or combination equipment, understanding how to properly size conductors is crucial for safety and performance. In this case, the outdoor unit for a multi-fan, multi-stage compressor commercial alternating current unit specifies a circuit minimum amps, or CMA, of 114.38 amps and a circuit maximum overcurrent protection, or CMOP, of 150 amps. The question arises whether to apply additional factors to the 114.38 amps value when selecting the conductor size. The answer is no, you should not apply any additional factors to the CMA value. The CMA value, as provided by the manufacturer, already incorporates the necessary factors to ensure the conductor has sufficient ampacity. This includes considerations for the type of conductor, such as THHN, and its corresponding ampacity rating. Applying additional factors would result in oversizing the conductor unnecessarily. National Electrical Code, or NEC, Section 430.25 directly addresses this issue. Section 430.25 states that the conductor ampacity shall not be less than the marked minimum circuit amps, or MCA. This means that the conductor you select must have an ampacity equal to or greater than the CMA value provided by the manufacturer. It does not imply that you need to further increase this value by applying factors such as 115% or 125%. The manufacturer has already taken these factors into account when determining the CMA. To illustrate this point, consider the example provided. The equipment specifications indicate a CMA of 114.38 amps. If you were to apply a factor of 125%, you would arrive at a value significantly higher than necessary. This would lead to the selection of a larger conductor than required, increasing costs and potentially complicating the installation process. Using the CMA value directly simplifies the conductor selection process and ensures compliance with the NEC. By adhering to the manufacturer's specifications and the guidelines outlined in NEC Section 430.25, you can confidently choose the appropriate conductor size for the application. In this specific scenario, where the CMA is 114.38 amps, a number 2 THHN conductor would be suitable, provided it meets the ampacity requirements for the installation. Always consult the NEC and relevant equipment documentation to ensure you are making informed decisions regarding conductor sizing and overcurrent protection. In summary, when dealing with equipment that provides a CMA value, use that value directly without applying additional factors. This approach ensures compliance with the NEC and proper conductor sizing for the application. The CMA value already includes the necessary considerations for conductor ampacity, simplifying the selection process and promoting safe and reliable operation of the equipment. When selecting conductors for electrical installations, it is imperative to adhere to the National Electrical Code, or NEC, which provides comprehensive guidelines and requirements for safe and effective wiring practices. Article 310 of the NEC specifically addresses conductors for general wiring, outlining permissible ampacities and installation requirements. Understanding the principles outlined in Article 310 is essential for ensuring that conductors are properly sized and installed to prevent overheating, insulation damage, and potential fire hazards. One of the key aspects of conductor selection is determining the appropriate ampacity, which refers to the maximum amount of current a conductor can carry continuously under specified conditions without exceeding its temperature rating. NEC Table 310.16 provides ampacity ratings for various conductor types based on their insulation material, size, and installation environment. These ampacity ratings are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit and up to 3 current-carrying conductors in a raceway, cable, or earth. When the ambient temperature exceeds 30 degrees Celsius, or when there are more than 3 current-carrying conductors in a raceway or cable, it is necessary to apply correction factors and adjustment factors to the ampacity ratings to account for the increased heat generated. Correction factors are applied to reduce the ampacity of conductors when the ambient temperature is higher than 30 degrees Celsius. These factors are provided in NEC Table 310.16 and vary depending on the conductor's insulation type and the ambient temperature. For example, if a THHN conductor with an ampacity of 75 amps is installed in an area with an ambient temperature of 40 degrees Celsius, a correction factor of 0.88 may need to be applied, reducing the ampacity to 66 amps. Adjustment factors are applied when there are more than 3 current-carrying conductors in a raceway or cable. These factors are provided in NEC Table 310.15b3 and vary depending on the number of current-carrying conductors. For example, if there are 7 to 9 current-carrying conductors in a raceway, an adjustment factor of 0.70 may need to be applied, reducing the ampacity of each conductor to 70% of its original value. In addition to temperature correction and adjustment factors, other factors can influence conductor ampacity, such as the type of insulation, the presence of harmonics, and the method of installation. Conductors with high temperature ratings, such as THHN and XHHW, can generally carry more current than conductors with lower temperature ratings, such as TW and UF. Harmonics, which are non-sinusoidal waveforms caused by nonlinear loads, can increase the heating of conductors and reduce their ampacity. The NEC requires that conductors be derated when harmonic currents are present to prevent overheating. The method of installation can also affect conductor ampacity. Conductors installed in free air, where they can dissipate heat more easily, generally have higher ampacity ratings than conductors installed in enclosed raceways or conduits. When selecting conductors for specific applications, it is important to consider all of these factors and consult the NEC to ensure that the conductors are properly sized and installed to prevent overheating and ensure safe operation. In addition to ampacity, other important considerations for conductor selection include voltage drop, insulation type, and environmental conditions. Voltage drop refers to the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Insulation type refers to the material that surrounds the conductor and provides electrical insulation. Different insulation types have different temperature ratings, moisture resistance, and chemical resistance. The appropriate insulation type should be selected based on the environmental conditions in which the conductor will be installed. Environmental conditions such as temperature, moisture, and exposure to chemicals can affect the performance and lifespan of conductors. Conductors should be selected that are suitable for the specific environmental conditions in which they will be installed. For example, conductors installed in wet locations should be rated for wet locations, and conductors installed in corrosive environments should be resistant to corrosion. By carefully considering all of these factors and consulting the NEC, electrical professionals can ensure that conductors are properly selected and installed to provide safe and reliable electrical power distribution. The National Electrical Code, specifically Article 430, provides detailed requirements for motor circuits and motor control circuits. These requirements are designed to ensure the safety and proper operation of motors, which are commonly used in a wide range of applications. Understanding the requirements outlined in Article 430 is essential for electrical professionals who design, install, and maintain motor circuits. Article 430 covers a wide range of topics related to motor circuits, including conductor sizing, overcurrent protection, motor starters, and control circuits. One of the key aspects of motor circuit design is determining the appropriate conductor size. The NEC requires that motor circuit conductors have an ampacity of not less than 125% of the motor's full load current rating. This requirement is intended to account for the motor's starting current, which can be significantly higher than its running current. The full load current rating of a motor is typically found in the motor's nameplate. Once the full load current is known, the minimum conductor ampacity can be calculated by multiplying the full load current by 1.25. For example, if a motor has a full load current of 10 amps, the minimum conductor ampacity would be 12.5 amps. In addition to the 125% requirement, the NEC also specifies minimum conductor sizes for certain types of motors, such as hermetic refrigerant motor compressors. These minimum conductor sizes are based on the motor's rated load current and are intended to prevent excessive voltage drop. Overcurrent protection is another critical aspect of motor circuit design. The NEC requires that motor circuits be protected against both overload and short-circuit currents. Overload protection is intended to protect the motor and conductors from damage due to excessive current draw. Overload protection devices, such as thermal overloads or electronic overloads, are typically installed in the motor starter. Short-circuit protection is intended to protect the motor circuit from damage due to short circuits or ground faults. Short-circuit protection devices, such as fuses or circuit breakers, are typically installed in the motor circuit disconnect. The NEC provides detailed requirements for the selection and sizing of overcurrent protection devices for motor circuits. These requirements are based on the motor's full load current, starting current, and type of motor. Motor starters are used to control the starting and stopping of motors. The NEC requires that motor starters be properly sized for the motor they control. The size of the motor starter is based on the motor's horsepower rating and voltage. Motor starters typically include overload protection devices to protect the motor from damage due to overloads. Control circuits are used to control the operation of motors. The NEC requires that motor control circuits be protected against overcurrent and short-circuit currents. Motor control circuits typically include control devices such as push buttons, switches, and relays to control the motor's operation. The NEC also provides requirements for the wiring and grounding of motor circuits and motor control circuits. These requirements are intended to ensure the safety and proper operation of motor circuits. Grounding is essential for providing a path for fault currents to return to the source, which helps to prevent electric shock hazards. By understanding and adhering to the requirements outlined in NEC Article 430, electrical professionals can ensure the safe and proper operation of motor circuits. This includes proper conductor sizing, overcurrent protection, motor starter selection, and control circuit design. The National Electrical Code, or NEC, provides specific guidelines for sizing conductors and overcurrent protection for air conditioning and refrigeration equipment. Understanding these guidelines is crucial for ensuring the safe and reliable operation of these systems. Article 440 of the NEC specifically addresses air conditioning and refrigeration equipment, outlining the requirements for conductor sizing, overcurrent protection, and disconnecting means. One of the key aspects of sizing conductors for air conditioning and refrigeration equipment is determining the minimum circuit ampacity, or MCR. The MCA is the minimum ampacity required for the conductors that supply power to the equipment. The MCA is typically found in the equipment's nameplate. The NEC requires that the conductors supplying power to air conditioning and refrigeration equipment have an ampacity of not less than the MCA. This requirement ensures that the conductors are capable of carrying the maximum current that the equipment is expected to draw under normal operating conditions. In addition to the MCA, the NEC also requires that the conductors be sized to account for the largest motor load in the equipment. The largest motor load is typically the compressor motor. The NEC requires that the conductors supplying power to the largest motor load have an ampacity of not less than 125% of the motor's rated load current. This requirement is intended to account for the motor's starting current, which can be significantly higher than its running current. Once the conductor sizes have been determined, the next step is to select the appropriate overcurrent protection. The overcurrent protection is intended to protect the conductors and equipment from damage due to overloads and short circuits. The NEC provides specific guidelines for the selection and sizing of overcurrent protection devices for air conditioning and refrigeration equipment. The maximum overcurrent protection, or MOC, rating is typically found in the equipment's nameplate. The NEC requires that the overcurrent protection device have a rating not greater than the MOC. This requirement ensures that the overcurrent protection device will trip or open the circuit in the event of an overload or short circuit, preventing damage to the conductors and equipment. In addition to the MOC, the NEC also allows for the use of inverse time circuit breakers for overcurrent protection. Inverse time circuit breakers are designed to trip faster for higher levels of overcurrent. The NEC allows for the use of inverse time circuit breakers with a rating not greater than 225% of the equipment's rated load current. This allowance is intended to provide additional protection against high-level overcurrents. The NEC also requires that air conditioning and refrigeration equipment be provided with a disconnecting means. The disconnecting means is a switch or circuit breaker that can be used to disconnect the equipment from the power supply. The disconnecting means must be readily accessible and located within sight of the equipment. This requirement ensures that the equipment can be easily disconnected from the power supply for maintenance or repair purposes. The NEC also provides requirements for the grounding of air conditioning and refrigeration equipment. Grounding is essential for providing a path for fault currents to return to the source, which helps to prevent electric shock hazards. By understanding and adhering to the requirements outlined in NEC Article 440, electrical professionals can ensure the safe and reliable operation of air conditioning and refrigeration equipment. This includes proper conductor sizing, overcurrent protection, and disconnecting means. When working with electrical systems, safety should always be the top priority. This includes wearing appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and hearing protection. It also includes following lockout/tagout procedures to ensure that equipment is de-energized before working on it.